Welcome to iLecture Online. Well, here's another one of our viewer request videos. I know that we get lots of requests and we don't put all of them on video, but this was a pretty good topic and I realized that we had not yet covered this on any of our videos, our physics videos, although we've covered most of the physics topics. So this topic deals with rotational motion and specific with the dynamics of the rotating rod. And so I thought that was a good example, and there's going to be several parts to this problem. We're going to start out by calculating the angular velocity and the centripetal, I'm missing an L there, centripetal acceleration of the center of mass. And so what we're dealing with here is we're dealing with a rod. We start with the rod in a horizontal position. It's attached to a hinge on the left here. Once we let go, the rod will begin to swing down. Of course, it will accelerate. And if it could then swing back and forth, of course, the rod would continue to do that forever if there's no retarding forces, if there's no friction, no wind resistance, and so forth. So we're assuming no friction, no wind resistance. So how do we do that? What's the approach of finding the angular velocity of the center mass as a function of angle? And of course, we also want to find the centripetal acceleration. So the way to do that is to use energy techniques. We could say that energy initial will equal energy final. And so since we're not inputting any work and we don't have any friction, we can leave those terms off. So that means that the kinetic energy initial plus the potential energy initial equals the kinetic energy final plus the potential energy final. So what we're going to do is we're going to call this point right here the potential energy equal to 0 point. So that the center mass starts at a higher potential energy and it ends with 0 potential energy, because that makes the problem a lot easier. So initially there's no kinetic energy because the rod is not moving, and the initial potential energy is going to be mgh, which is equal to the final kinetic energy. Well, in this case, we're going to have rotational kinetic energy, so that's going to be 1/2 times the moment of inertia times omega squared. So instead of having 1/2 mv squared, we use 1/2 I omega squared, because we're going to account for the rotational kinetic energy. And then the final potential energy will be 0, because that will be the 0 height, the 0 potential energy point. All right, notice we've already here calculated the delta H. It starts from this point, it drops this far. Notice that from here to here, that's half the length of the rod, that's L over 2. And if we take that hypotenuse and multiply times the cosine of this angle right here, that's the angle theta right there, then we get this height. So we have L over 2 cosine theta as the change in height, or the beginning height. So we have m, which is the mass of the rod, L is the length of the rod, so we have m times g times L over 2 cosine of theta is equal to 1/2 times the moment of inertia of a rod that rotates about its end is going to be 1/3 the mass of the rod times the length squared, and then we multiply that times omega squared. Of course, in this case, we're trying to solve this for omega. Notice that the 1/2s can cancel. The mass can cancel on both sides, so that gives us a simplified equation of GL cosine of theta is equal to 1/3 L squared omega squared. And then I just noticed that this L will cancel out one of those L's. So now we're left with G cosine theta equals 1/3 L omega squared. And then if I solve that for omega squared, we now have omega squared as a function of theta is equal to, bring the 3 across, we get 3g times the cosine of theta all divided by L. And we're going to leave it as omega squared. Instead of omegas, we're going to use omega squared later in our other equations and other calculations. So that gives us a function of omega gives us omega as a function of theta. So let's do some limiting checks real quick. What if the angle is 90 degrees? If the angle is 90 degrees, the rod is up here, the cosine of 90 is 0, that means it's not moving yet. That makes sense. And if the angle is 0 degrees, when the rod is vertical, then the cosine of 0 is 1, then omega squared will be 3g over L. Notice that there's no effect because of the mass, but there is an effect because of the length. So, well, that's because if the rod is longer, the center mass will be farther away from the point of rotation, and that means that the rod, or at least the center mass of the rod, will be moving faster. Remember, this is for the center of mass of the rod. In dynamics, we can always take the center mass as being the point on the object that does the motion. Everything else kind of is along for the ride. Okay, now let's see. Now we want the centripetal acceleration. So we have an equation for the centripetal acceleration. So acceleration sub c, centripetal acceleration, is equal to v squared over r. Now what we have to do here is convert omega to v, and so we can say that omega, well, let's see here. Let's try it the other way around. We can say that the velocity is equal to the radius times omega. That means that omega is equal to v over r. So that means that this, well, actually we could say v squared is equal to r squared omega squared. That's even better. So we can replace v squared by r squared and omega squared. That's why we kept omega squared. So this can now be written as r squared omega squared divided by r. And then if we cancel out this r and that r, we can say that the centripetal acceleration as a function of the angle is equal to r times omega squared. That's it, like this, all right? And finally, if you want, you can then replace omega squared by this. So you can then say that the centripetal acceleration is equal to, and r, of course, can also be written as L over 2. Let me write that as well, because we may want to write it in that form. So we can say that the centripetal acceleration as a function of theta is equal to L over 2, because the radius of the rotational motion for center mass is half the length of the rod. So we have L over 2 times omega squared. So that's another way of writing the centripetal acceleration. And then replacing this by this, we get centripetal acceleration as a function of theta is equal to L over 2 times 3g cosine of theta divided by L, and then notice that the L's cancel out, so you can also write the centripetal acceleration as 3 over 2 g cosine theta. Notice that in this case, the centripetal acceleration has nothing to do with the length of the rod, nor does it have anything to do with the mass of the rod. Simply 3/2 g times the cosine of theta. Again, let's do limiting checks. If the angle is 0 degrees, so when the rod is up here, like this, 0 degrees, sorry. When the rod is like this, right, so it's vertical, then the cosine of 0 is 1, and the centripetal acceleration will be 3/2 g. When the angle is 90 degrees, when it's up here, the cosine of 90 is 0, centripetal acceleration will be 0. So that makes sense. So here we have omega squared as a function of theta, and the centripetal acceleration as a function of, not a, but theta. And that's a good start on understanding what is happening with this rod. Next, we're going to also calculate some of the forces that are on the hinge, and maybe some other things as well. So we'll do 1 or 2 more videos to get a full understanding of the rotational dynamics of a rod.